Hi, my name is Przemysław Koprowski and this is the first part of a mini course of SageMath, or Sage for short. Today I will show you some very basic operations that you can do in Sage, some basic calculations that can be done using SageMath. SageMath is a general purpose cross-platform system that can be run on basically every modern operating system, be it Linux, Windows or MacOS. The program itself is quite bulky. It occupies nearly 10 gigabytes of disk space, at least on my computer, so it takes some time to both download and install it. Moreover, the first time you run it, it needs to initialize many things, so the first run is quite slow. However, fortunately, after this first time, every other time you start it, it will run much faster. So now I will show you how to use Sage in the very basic way, how to do some basic operations. Once you finally started Sage, it opens a web browser and takes you to Jupyter, which is nowadays the default front end for Sage. You can then either select and open an existing file, or you can create a new one, clicking the new button near the top right corner of the screen. That's what I will do right now, so I will create a new notebook, new Sage notebook. Every Sage notebook consists of a number of so-called cells. When you create a new notebook, it just contains one empty cell. And everything you want to compute, you must enter into this cell and execute such a cell to get the result of these computations. Let me start with a most basic example we can imagine. I will type just 2 plus 2. Now, to evaluate that cell, to get the result of this computation, you can do one of two things. You can either press the run button, which is located here near the top of the screen, or you can press Shift Enter. Personally, I prefer the second method because when I type something, I already have my fingers on the keyboard, so it's much faster, much more convenient for me to just press Shift Enter than to move my hand from the keyboard to the mouse and then click something on the screen. But it's basically up to you. Both methods do exactly the same, so if you either click the run button or you press Shift Enter, you get the result. Sage will evaluate the cell that you are in, and it will produce the result of these computations. So I will do it right now. So I will press Shift Enter, and as you can see, the result is of course 4. Okay, this was trivial. Let's try to do something more challenging. So suppose we want to compute the value of the following formula. So I will type the formula into Sage. So I will type 0.25 times square root of the sine of 0.4488, and now we need to add 0.75 times cosine of 0.1274, and this is to be the numerator, so I need to put everything in parentheses, and it should be divided by the denominator, which in our formula is 1 plus e to the power 1.625. So again, I will press Shift Enter, and Sage evaluates the formula, and Sage calculates that the formula is roughly 0.15. And now I will do one more example. This example will be a bit different, so you will learn some new things. So suppose that this time we want to evaluate the following formula. Cosine of pi over 9 plus sine of 8 over 9 pi and everything is divided by cosine square of pi over 12 minus sine square of pi over 12. So again, let me type the formula. So we have the numerator is cosine of pi over 9 plus sine of 8 over 9 times pi. This was the numerator, and now the denominator is cosine of pi over 12, where everything is squared, minus sine of again pi over 12, and we need to square it. So let me now evaluate the formula. As you can see, what we got this time is not a number, it's just another expression. Sage rearranged the terms a bit and outputted another mathematical expression, not a number. The reason is that in the previous example we had floating point numbers. We had a number 0.25 or the number 0.75 and so on. So floating point numbers are, by its very nature, are only approximate. The very nature of floating point numbers is that they represent some numbers only approximately. So when Sage encounters a floating point numbers, it knows that the the result will be only approximate. So it evaluates the formula numerically. It produces the floating point numerical approximation of the result. On the other hand, in this second example here, we have only exact numbers, only exact rationals, like 1 over 12, like 1 over 9, and so on, and we have some symbolic entities like pi. So everything in this formula is exact, and so Sage tries to preserve the exact value as long as possible. So if we don't tell Sage to give us a numerical approximation of the result, it will try to keep the exact value of the formula, and this is the reason why it does not produce a number. It produces just another formula, because it cannot do much with this formula. It's too complicated to get it is not a rational number, so it is just some expression, and that's what Sage outputs. To get a numerical approximation of this formula, I will do the following. First of all, I will assign this formula to a variable. This is not necessary, but it's more convenient to do it this way, so it will be easier for us to work if we call this formula somehow. So I will assign this formula to a variable w, and if we produce the w as an output, we see that we have exactly this formula. You can think of it as attaching a label to the formula. So we have some formula and we attach a label w. So every time we use w in our expression, in our Sage session, then this w will mean exactly this formula. Now if I want to evaluate the formula numerically, if I want to get a numerical approximation of this formula, I can type w.n. n stands for numerical. So I will write w.n and empty parentheses, and now when I evaluate it, it takes a moment, and the result is 1.48 approximately. We may also specify our desired accuracy. We can say, for example, that we need just 4 digits. We don't need more than 4 digits. To this end, we just use an additional parameter, an optional parameter of the function w, and we write digits equal to and the desired number of digits that we want. So, for example, I want 4 digits, so I will type w.n and I will write digits equal to 4, And when I evaluate this time, I got just 4 digits of the result. There is also another method to get a numerical approximation of the formula. The second method is somehow more general. It is not used not only to get the numerical approximation, but to generally convert representation of objects between different types. Generally, every object in Sage belongs to some structure. So there is some parent structure to which this object belongs. We can get this parent structure if we type object.parent. So in our example, if I type w.parent, then the result is symbolic ring. Symbolic ring because it is a symbolic expression. On the other hand, if I type, let's say 0.25 or any other floating point number, dot parent, then the result, as you see, is the real field with 53 bits of precision. In Sage, this field is shortly denoted RR because this double R resembles double stroke R that is normally used to denote real numbers in a mathematical text. So if I want to convert W from the symbolic ring to the real field, I will just type RR and W like this. RR of W. This means that we want W to be expressed as an element of the field of real numbers, of floating point approximate real numbers. So if I evaluate it, I again get the numerical approximation of the formula W. The table you can see on the screen right now collects some of the common rings we can use in calculations and the corresponding Sage commands. So for example, the field of rational numbers is QQ because QQ resembles the double stroke Q used to denote rationals. To see how this conversion between different types of object works in practice, let me take, for example, a rational number, let's say 3/5. So 3/5 is an exact rational number. If we type it, we get the rational. If we want to get the floating point approximation, floating point representation of this number, we can type RR of 3/5. And so the result is 0.6. On the other hand, if we type QQ of 0.6, then we take the floating point number and we convert it into an exact rational, so we get back the 3.5. One thing that you should be aware of is that this conversion is not always reversible. If we take, for example, an integer 12 and we convert it into a Galois field with, say, 7 elements, then the result will be 5. Let's see. So we have an integer 12. It's I will denote this A. So A is 12. It's an integer. We can check it by evaluating the parent command, parent method. So we see that A belongs to the ring of integers. We can convert it and represent it as an element of the Galois field with just 7 elements. So if I evaluate GF7, so Galois field with 7 elements on A, the result is 5. The result is 5 because 12 modulo 7 is 5. On the other hand, if I now try to lift this 5 from the Galois field back to the ring of integers, there is no way I can retrieve 12 because both 12 and 5 they map to the same element in the Galois field. So Sage will not be able to retrieve 12 because some information is already lost. So let's see, if I now convert the last result to the ring of integers. So this is the ring of integers, and the underscore means the previous result. So we got 5. We don't get 12 because this is not one-to-one. This is not one-to-one. So in this case, the conversion is not reversible. So we can convert from the ring of integers to the, let's say, the Galois field. And we can convert the other way around. We can lift elements from the Galois field back to the integers. However, the two rings are not in one-to-one correspondence, so this conversion is not reversible. The last thing that I want to show you is how to operate on symbolic expression in Sage. Sage is not limited just to numbers. It can work with numbers, but it can work also with symbols. So, for example, we want to simplify, to evaluate the formula that looks like this. Here A, B, C and D are some symbolic variables, and I is the square root of -1. The first thing that we need to do is to declare all the variables which appear in this expression. There are 4 variables here, A, B, C and D, because I stands for the square root of -1. So Sage already knows that I square is -1, but A, B, C and D are just symbols. So we need to tell Sage that these letters represent some symbols, because otherwise Sage would be in lost. There is more than one way to do it. I will show you just one way. One possible method is to type var and then the names of the variables separated with commas in quotation marks. So let me write it like this. Var is an abbreviation on a variable. This means that everything I type here should be treated as a variable. A, B, C and D are some new variables. I can now type the whole formula, and I will again assign it to the variable W so we can operate on it. So I will type that W is this formula. So we have A plus I times B times C over A square plus B square plus I times D over I minus A minus I times B. Yeah, this is the first parenthesis, and we need to multiply it by the second parenthesis, which is C minus I times D times A plus minus I times C minus D times B. Now we can type W to display this formula. By default, Sage displays the results of its computation in text mode. This is convenient if you want to copy and paste some part of this result, some part of the answer, and paste it into a new cell to do something with it. However, it is not very human readable. So if we want to see it better, see it in a nicer way, we can pretty print it, we can typeset the result using the command show. Show uses LaTeX typesetting system to pretty print its result. So it takes the result, sends it to LaTeX, then LaTeX formats it, and show displays it on screen. So if I type show of W, then we have this formula presented in a nicer way. We can use this command directly, like you can see right now on the screen, or in a more elaborated way, we may write show of, and now in quotation mark, W is plus LaTeX of W. This way we prepended W equals to the formula itself, so we can see that this formula refers to W. This second method is more convenient if we are working with more than one formula at the same time. So we can label this formula, we can see which formula is displayed in which part, so we can keep track of which formula is which one. So far we have done nothing with the formula itself except displaying it on screen, but we can try to simplify it. Sage offers a variety of different methods to simplify algebraic and symbolic expressions. I will show you just one of these commands. It is called simplify full. So I can type w.simplify full and empty parentheses. Now you see that the output is c squared plus d squared. So Sage simplified this formula. Sage applied some different elementary algebraic operation to the formula and found out that the formula actually is independent of a and b. It depends only on c and d, and the result is just the sum of squares of c and d. We can display it like this in the text mode, or we can again use the show command, and I can write show of w.simplify full. And now Sage displayed it, typeset it using LaTeX backend. Beside the simplify full command, Sage offers a variety of other commands that can be used to simplify or manipulate algebraic and symbolic expressions. In fact, the number of all the commands that Sage offers is so huge that I doubt that anyone can actually remember all the names, and honestly speaking, it is not necessary to remember these commands, because there is a simple way to find the command that you need right now. If you type the first few letters of a command, so you suspect that simplification will be something that starts with SIMP, and then you type tabulation button, then Sage will display all the methods, all the commands which starts with a given letters. So if I type w.simp and I press tabulation, then I see the list of all the commands that can be used to simplify the expression w. One of them is this simplify full that I used before. If I type just w dot and I press tabulation, then I'm presented with a very long list of all the commands that can be used with w. So you see that this list is huge. There are lots and lots of commands, and all these commands can be used with w. Simplify full was just one of these commands. Two very useful commands that can be used with symbolic expressions are factor and expand. These commands are basically opposite to each other. Factor tries to express the formula as a product of some simpler formula, as a product of parentheses, as a product of prime numbers, of prime elements, or of irreducible elements. And expand does the opposite work. It multiplies everything and it expands the formula as long sum as possible. I will try to explain how these two commands work using a very simple example of the formula a squared minus 1. So, for example, if I factor the formula a squared minus 1, what I get is the product of two linear terms, a plus 1 and a minus 1. On the other hand, if I expand the last result, recall that I said earlier that underscore stands for the last result. So if I type expand underscore, mean I want Sage to expand the last result it returned. If I press Shift Enter right now, I get back the a squared minus 1, so it expanded this product of two parentheses into an explicit sum a squared minus 1. So these two commands are opposite to each other, as I said. The factor and partially also expand commands can be used also with other objects, not only with symbolic expressions. We can factor, for example, polynomials, or we can factor integers. We can factor integers into products of powers of prime elements. So just to conclude this video today, I will factor the today's date. I'm recording this video on the 10th of March 2022, so let me factor this number. So I will type factor of 2022 March 10, and you can see that this is a product of prime numbers 2, 5, 11 square, 17 and 983. Today I presented a couple of very basic, very elementary functions that can be used in Sage to just use Sage as a big calculator. And next time I will show you how to use Sage for some calculus, to compute limits, derivatives, integrals and things like this. So I hope you enjoyed this tutorial and see you next time. Thank you.